So, hi everybody. It's Tuesday, 6 p.m. Here in Israel again. And today we are going to discuss foundation models. And I will try to also follow a bit on the concept of transformers, so that this lecture will be a whole. You can really start from fresh. Foundation models are really one of the hottest topics nowadays, everywhere in the medical field and also in pathology. So it's really a very, very exciting frontier of artificial intelligence. I think that from my point of view, really AI has changed dramatically in the last 3 years. So being in the computer vision industry for, I don't know, for 3 decades or even more, I think that the jump that we've made in around 2022 is unbelievable. I could see how things that we struggled to achieve back in 2014 were then resolved in 2017 much easier with deep learning, and now things that we struggled to achieve 5 years ago really struggled and failed. Nowadays, you can really achieve in a way that is really beyond the expectations, both in terms of quality and speed. And a lot of it is thanks to the availability of foundation models. So without any further ado, let's kick off to this session. I will share my screen. One moment. And okay, here we go. So just okay. So actually I'm not using my course format because I'm relying on a presentation that I gave for in a few companies a while back, and so changing the format was a bit too tedious, and it's nice to have like a darker background. So but still, it's going to be very educative, not promotional. Okay, so and again, of course, any question in the middle, I'll be happy to try to answer. So medical imaging, specifically pathology, as you can see here, but also other domains such as CT and MRI and ultrasound. We have a lot of challenges, and we want to be able to quantify things, to detect abnormalities, to assess the size of things, to estimate whether things are having any pathology or are fine. And the domain of medical imaging really was under a lot of R&D for many, many years, and each time we progress and create new solutions, et cetera, et cetera. So, and foundation models really arrive to each and every of these domains. So foundation models are really not specific to pathology. They are not specific to vision. They are in a much larger context, but they can be found in any of these domains. Now, as I told you, I really witnessed firsthand the evolution of computer vision, of the computer vision domain, where in the classical computer vision area, the era where I was a student during my PhD and my postdoc, etc. So specifically, I was dealing, by the way, with the Gabor analysis. So the analysis of images via Fourier-like filters, and this was pretty hot in the beginning of this century. Also bilateral filters, which are classical and amazing mixture of Gaussians, and also SIFT, Hogg, Viola Jones, For those of you who might come from the computer vision ecosystem, these are really classical, like classical music. And these tools are really powerful and you can solve a lot of things with them. But back in 2012, 14, 15, we started the classical deep learning era. And this era we discussed in a lot of details in the first 3 lectures of our session here. You have like your layers and features generation, and you are training, you are manipulating and tuning the parameters of this deep neural network to be able to solve a specific problem, being it segmentation, detection, prediction, whatever is the problem that you want to solve. So we went through some classical architectures. One architecture that really survives the the agony of time, so it gets old in a pretty nice way. And getting older in the AI domain can be a matter of months. And here we talk like about UNet, which survives pretty nicely over almost a decade, which is, I think, exceptional. And by the way, I really, really love UNet. I gave a lecture once on the similar, because I'm coming from classical computer vision. So, I'm also a mathematician. I always like to take things and try to project them on things that I already know. And UNet definitely reminds me of a very classical paper from the 80s, which is called Laplacian-Gaussian pyramids. Those of you who are mathematically inclined, there is a lecture on that. I will ask Masha tomorrow to add a link, but this is really for those who have mathematics. Now, even in the classical deep learning domain era, there is a very important concept which allows scalability of deep neural network. And this concept is the concept of transfer learning. And this is super important because it serves as, I would say, a foundation for what we are going to talk about in this session. So again, we have input, we have all blah, 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 all of these layers, and the convolution layers, extracting features, okay. Then we have a huge set of features, like a box of features. And from this box, we start detecting and dictating some kind of analysis, the fully convolutional part to make decisions. So when we look at network A, we can divide it into 2 parts. The first part is the generation of the features space. And from the features, so this generation of the feature space is via application of convolutions and typical machine learning, I would say, operations, and the decision. Now, let's say that I trained a very good neural network on, just natural images, birds, countryside, I don't know, buildings, etc. So, and I trained it a lot to be able to distinguish between cats, dogs, birds, waves in the sea, whatever. And I have a lot of images, so I have the privilege in natural images. I have a lot of images out there, and I really trained a very nice network A. And now I have a new challenge, pathology. And in pathology, let's say that for some reason, I don't have access to so many images. Okay, I have access to a limited number of images. So it will be very hard for me if let's say I want to do to solve a segmentation problem, to distinguish between a tumor and stroma and necrosis, and I just don't have enough information. So one option is to say, I can't do that. The other option, and this is an option that several companies and institutes have been taking in the last few years is to use transfer learning. What does it mean? It means that I have a similar task of dealing with images, natural images, not necessarily pathology images. But I trained the neural network to be able to extract important, meaningful features that can be used to solve a specific kind of problem. So I can tell myself, okay, pathology images are also images. So what if I would transfer the parameters of this part of the neural network, put them in network B. So I have a box, I have a box of parameters, and so maybe I can use the parameters extracted with the layers taken from network A. Maybe I can only train this part of the decision making of the neural network to make the right decision for pathology images. And this approach is working. It is working. Of course, we have to account for the fact that, first of all, we have to see how close the domains are. Are pathology images really so close to natural images? Do we need, in order to have a decent result, do we have to retrain, because we still need to retrain this? Do we need to retrain on thousands of images or millions of images? And also, does it make sense if I do get access to a little bit more, let's say, quantity of pathology images, maybe I can also train a little bit of this part of the features extraction. So all of these are very good questions, and they are open questions that you can answer when you have information on the amount of data that you have, on the let's say the degree of accuracy that you want to achieve. So this is really can change, but the concept of transfer learning is very strong. I am able to train a network or take someone else's network, for example, and then use part of the network as my skeleton for the features extraction. So these guys, the orange and the green boxes, we call them the feature space, embedding space. And the meaning is that in this part, we have learned to extract meaningful information from our data. So the concept of transfer learning already exists for many, many years, so there's nothing new. Please keep it in mind because it reappears a bit later when we advance in modern AI. Now, in pathology, you see that exactly what I suggested. Well, I'm not original. Someone else thought about it before. Back in 2019, Ponzio et al. Dealt with the lack of training data. They took the ImageNet. Do you remember the ImageNet? ImageNet was the network developed, I'm sorry, the dataset that was developed by Professor Fei Li and her students to serve the competition of classification. So it was available. So you could take ImageNet, okay, use this part. So use part of ImageNet where the parameters are frozen. So it's like the very, very first low-level features are not like edges, lines, corners, dots. All of these things are super basic structures which are not unique to cars, tumor cells, etc. They really are super basic. So you take some of the weights already trained, someone else did the work for you, and you are training only part of the convolutional layers and the fully connected layers. And this seemed to work pretty well. Now, foundation models entered our life, the term foundation models entered our life back in 2021, so 5 years ago in Stanford, where they published a paper on the opportunities and risks of foundation model. Now, a few famous examples of foundation models would be ChatGPT, would be Claude, would be Gemini. So all of these are foundation models, by the way, not for vision, but rather for language. And this is like, I want to say something here. Large language models are super advanced. They are really, and I think all of us benefit from that because I'm sure that all of you in the crowd, in the audience, use one of these tools on a daily basis. We negotiate with these tools. We get advice. We try to fine tune what we have to say, and we polish our presentations, etc. But then vision foundation models are also super advanced, but they are still, I would say, they are still one phase behind large language models. Now, what are foundation models all about? So, foundation models are deep neural networks. Okay, deep neural networks that are pre-trained on vast amount of data. So, if you after this talk, if you say, okay, Chen convinced me, I want to create my own foundation model, I wish you a lot of luck. You need to have a lot of data. You need to have the will and ability to pay pretty high electricity bills, and also to arrange for yourself a nice, I would say, farm of GPUs to enable the training. The idea is that we are employing deep learning architectures with billions of parameters. So just to give you an example, we recently used in our DeePathology studio 6 or 7 billion parameters model to enable a capability that I will share with you on our last session. This is still under the radar. So it's really billions of parameters, and this allows us to capture delicate patterns and structures in our training data. So once we train our foundation model, then you could give it away for free, as some institutes and companies do, or ask for money for it, which is also fine. And then as a user, you're taking the foundation model, and it's not like you have to do something. You are actually taking the box. You are taking this box that was generated by the foundation model, and you are using this strong tool of features generation to create a specific solution. So you need to fine-tune what foundation model brings to achieve and to complete a task-specific tasks on specific data sets. Okay, I think I saw a question, so let me just quickly, okay. Hi, Efrat, how can you tell which layer is for which task? It seems very important to transfer link to freeze the graph. Wow, Efrat, you're asking such a great question. The honest answer is I have no idea. But if we are zooming out and looking at it, you have to consider how similar would be the data that was used for the training of the foundation model and your own data. The more similar they are, the more you can concentrate only on the decision part of the deep neural network, so on the fully connected layers. But if there are differences, then you need to somehow involve in the retraining machinery also the features extraction part. And you really have to assess it from the similarity and try, I would say, to try to see what would be the minimal work you have to do in order to create a solution which suits your metrics. So you can take an approach, a phase approach, and start from having I would say delicate changes and adaptations, and move forward the more robust and accurate results that you need. Okay, now, for example, when we look at Google Translate, can I have a coffee and tiramisu? Posso avere un caffè e un tiramisu. Now, this is basically another, you remember that we talked about a translation from language to language, and nowadays it's really a task which is, I think, super trivial for all of us. But I was trying to use text translation like a decade ago, and it was super terrible. So for me, it's far from being trivial. And having these predictions also relies on a huge foundation model which learns the connection between one language and another. So foundation models provide features. They provide, but this is true to any deep neural network. Any deep neural network, the first few layers or the first a lot of layers, they provide features. So what's the difference? The difference is that we in a task-specific deep neural network, we usually train it on, I would say, much smaller data set than we use for foundation models. So the features are, I would say, are tuned to adapt to the task in mind. In foundation models, you are not training for a specific task. You are training to capture and understand the data. So the features that you are obtaining are hopefully a good representation of the data. So when you are shopping around for foundation models, the question that you should ask yourself would be, how well this foundation model represents the data. And there are some review papers that try to compare the capabilities of foundation models, also in pathology. And the thing is that the proof is in the pudding. How can you know whether one foundation model is better than the other? Create a benchmark of tasks that in order to achieve them, you take the features from the foundation model, see how well each and every foundation model is extracting enough information from the data in order to achieve this task. And this is how you can compare foundation models. Now, it's very difficult to do it by yourself because it's a lot of work. And this is why there are some papers who do that. So I want just to add here, so because I want to write. So for the email tomorrow, there is the lecture that I want to send you. I don't remember if it's in Hebrew or in English, but anyway, you can use Google Translate, and also some kind of a review and comparison of foundation models in pathology. I read a few papers, and I really think it's nice to, if you wanted to just get a bit more insight about the differences in foundation models, because it's not trivial to say this one is better than the other. Okay, so if I have a foundation model, how do I use them? So the first thing that we get from foundation models is the creation of a high-dimensional embedding space that captures the meaningful information, and this embedding space can be tuned to new tasks. This involves further training, so in principle, you might need a data scientist to use supervised learning on smaller data sets in order to create the model. Try to imagine what happens when this data scientist is part of a platform. What platform? You guess. Now, you all know that one of the most annoying tasks in creating deep neural network solutions is annotation. Annotations for supervised machine learning. Supervised machine learning means that how do we know how to train a system? Remember, I think this was already in the first session. Let's say that we want to compare between cats and dogs. Then when the system predicts if this is a dog or a cat, someone has to sit at the end of the neural network and say, correct, or no, it's wrong. You need the ground truth. And also in pathology, if you want to detect tumor cells, someone has to create the ground truth and to do annotations. And this is really a super, super tedious task. And there were things to alleviate this effort. We used, for example, active learning, and there were other methods to do this quickly. Now, you can ask yourself, if for foundation models, I'm training a neural network which has billions of parameters. So billions of parameters means that I need to have a lot of data. And if I have a lot of data, it means I have to have a lot of annotations. And just for example, a few years back, there was a very important paper by PathAI, really a classical paper in pathology, where they discussed how they were able to find what they called HIFs. HIFs are human interpretable features. This was before the era of foundation models. And in order to do that, to generate the human interpretable features, they had a lot of annotators having to annotate. So for foundation models, you need to have all the pathologists in the world sitting and annotating rather than doing research and diagnostics. And this is, of course, not possible. So in order to train foundation models, methods which are called self-supervised learning were developed. And these are super neat approaches because they mean that you don't need to annotate. How this is possible that you don't need to annotate? So instead of relying on human labeled data sets, the system learns from its own data. What does it mean? It means that we are let's start from the second example. Okay, masked image modeling. Take an image, okay, and delete part of it. And one time you delete this part, now delete this part. Each time you delete another part. Now, what would be the training process of the neural network? You would try to predict the missing part. So try to imagine you have as input an image where part of it is small, part of it is missing, and the system learns to recover the entire image. Now here you can do it automatically because you know exactly which part of the image you took off. So the ground truth is obvious. So this is a way to not to teach the system to complete images. This would be like a side effect of the process. But the real benefit of this approach is that the system learns the features of your images so that it knows how to complete them. And this is when you do this trick for billions of images, then it allows you completely in a self-supervised manner to learn the representations of your data without having a human in the loop on one end and being super accurate on the other end. So this is super cool. I mean, just think, it's so simple and yet super clever. Another thing is called contrastive learning. Now, what does it mean? It means that, again, it can be very automatic. We have two images, let's say, taken from two different slides, and we take patches, and we know exactly where we took the patch from because we control that automatically. So the input to a neural network would be two patches, and what the neural network should be doing is to say whether these patches were taken from the same slide or from the same type of cancer or from the same staining, etc. I hope you get the idea. Or is it different? And again, this classification, and okay, the ground truth, we know because we know from which slide we took the patches. And the classification between slides would be a side effect of this process. And again, the most important part of this process would be to learn the embedding space, the feature space of the data. So this is a super important trick because if we hadn't have these self-supervised learning mechanisms without having people in the loop, this would be mission impossible. Okay, it would be just too big, too huge to annotate all of these things manually. And so if we try to compare for a minute how foundation models are different from usual AI models. So in traditional AI models, you need really labeled data sets for each specific task. For cells detection, the annotations of cells, tissue segmentations, annotations of tissue. While in foundation models, we do train our models on huge data sets, but using a self-supervision. In traditional AI models, we could try to generalize a neural network that was developed for one task to another task. From my experience, it's far from being trivial because when you develop an application for a specific problem, you really need to retrain dramatically when you go to another task. In foundation models, the idea is that you can use foundation models for a variety of tasks because what you obtain would be the feature space, and from that you can go into many directions. And of course, in traditional AI models, let's say that I developed a fantastic model to find beta amyloid plaques. Okay, so I need access to beta amyloid plaques, and maybe I don't have a lot of slides, and maybe these slides are stained in a specific way. And when I try to generalize that, I have a big problem. Foundation models, to start with, are trained on a lot of data, and therefore they are easier and potentially much, I would say they are much stronger in scalability. And this is super important. Foundation model should be able to allow us to use it for many downstream tasks. Well, as I told you, building foundation models, you need to fund it. You need to fund it because you need to pay for data, you need to pay for compute power, you need to pay for electricity. So we are not going, for example, to anytime soon to develop our own foundation model, but being a legitimate user, of course, of foundation models is very clever because you are using the work of someone else that did all of the work of extracting features, blah, 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 etc. And you are now using it and just you have to train a much, much smaller problem. So it's a good idea to use foundation models for your own tasks because it means that you get like the basic sophisticated features extractor, and from that you can do whatever you like. Now, foundation models are usually relying on transformers, and we had a session on transformers last time, and the transformers, just to give you a quick reminder, we have encoders that look at data, take the data, it took some kind of feature space, but not in a simple way, but in a way where we also look at where to focus our attention. So we look for the relationship between the components of our input data, and then we decode this information in order to solve a specific problem. So transformer, usually foundation models are, or in order to be a legit foundation model, you need to use transformers. And again, just a quick reminder, when we talked about transformers last time, we first looked at the recurrent neural networks. So we have some kind of a consecutive process where each phase also impacts and provides information for the next phase. We called it RNN. And if you recall, we said that RNNs have a memory problem. So we wanted to balance the long and short memory using LSTMs. And I will skip this example. So LSTMs and RNNs, we have some input, we have the encoder network, and then we are getting some kind of feature space, and then we decode it to the result that we want to have. Again, a lot of credit to the authors of the seminal paper, Attention is All You Need. And this is not taken from this seminal paper, but from the paper of Badanu. I'm sorry if I forgot the name. I should have put the reference here. And if you recall, I really, really like this image because it really shows that we are taking all the information, we're taking all the connections here, and we weight them in order to provide the next output. So the attention mechanism, I would say that even in classical computer vision, in classical deep learning, it plays a super important role, but definitely in modern AI when we are talking about the age of transformers. Now, so this is like another way of looking at what we call self-attention. Self-attention would be to find a relationship between our inputs in order to generate the outputs correctly. And when you take these mechanisms and you put them as a big block, and you are putting all of these blocks together, then this is the problem with mathematics. You take super simple things like 1 + 1 = 2, and then you build upon that something more complex and something more complex and something more complex. And finally, you get something which is so complex that you are tending to say, what is this monster? And you have to remember, mathematical monsters are made of much, much smaller, pinkier, and not scary at all monsters. So even when you see that, the idea that it builds up on simple rules and logic. Okay, so in the remaining time, I'm going to talk about practical things. How were foundation models generated for pathology, and give you a few examples. So Dino is a super important foundation model. It's self-supervised, and it was introduced in 2021, so only 5 years ago, by researchers at then called Facebook, nowadays Meta. So Dino aims to relate global views of images, how you view images globally. And now this global view of an image is related to the local information in the image. They do that using two networks, a teacher and a student, same architecture. And the idea is that the images goes through cropping of smaller parts and larger parts, and we try to find the relations between the parts. And again, the aim here is not to find the relations between parts of the image in different scale, but to capture the data and the representation of the image. Another very important foundation model from Meta is segment anything, SEM. We have SEM1, SEM2, SEM3. I can tell you that these are super powerful tools. Again, the idea is that, as the name implies, you can segment anything. You can put dots in an image, and it will segment the objects around them. This was learned on a lot of data. And what's super kind of nice of Meta is that both Dino and SEM are available to use. So you can go and use them tomorrow. A very nice project that I do for the community, which is not related to pathology, but related to the analysis of videos in laparoscopic surgeries, together with Professor Yoav Mintz from Hadassah Ein Kerem in Jerusalem, is to try to detect all the objects that you put inside and out in a laparoscopic operation. And one of the and we had like a course 1 year ago, and 1,000 participants, which was amazing, and 170 people who were interested in doing projects for the community. And one of the projects really used these foundation models to allow tracking of objects in these laparoscopic videos. And I can tell you firsthand, in an effort that we did back in 2022, having object detection without SEM was really much, much more difficult and much less robust. So for me, and I think that for many people in my community of computer vision, having these foundation models is really a game changer. Really, really a game changer. Other vision foundation models is something like the Vitami model. This is also a way to show how you train this model. So you see, we take image where some things are missing. We have the encoder to create the feature space, the decoder to try to create the original image. You remember how we called that? We called that autoencoder. And we said, yeah, this is a super silly task because you want to create from the input the output. So here it's like a modified autoencoder, because here you have some parts of the image missing. But again, it's not the task which is important, it's creating this guy, the feature space, which is important. Now, foundation models are not only available in pathology. They are all over the medical imaging space. And we have foundation models for a CT. This one is from the National Cancer Institute. And the idea is to have a foundation models that you can use to analyze the CT images. But when it comes to pathology, I'm giving really a lot of credit to Faisal Mahmoud from Harvard, who is really, I would say, a factory of creation of foundation models. So really kudos to Professor Mahmoud. So in Mahmoud's lab, what did they do? They said, okay, we have Dino and Dino 2. This is fantastic. So we have a great thing to start with. But still, this was trained on trees and dogs. We want something specific for pathology. Now, they had the opportunity to have access to 100,000 pathology slides, generate over than 100 million pathology patches from them. So what they did, they took the foundation model of Meta, Dino and Dino 2, and they retrained not only a small part, they retrained, they retrained it, not fully, partly, but they retrained it to extract the extra information from pathology slides. And this foundation model, they could use it. So what did they achieve? They achieved a very strong representation of pathology images using the foundation model of Meta and retraining on their own pathology data. So they could use this. And just remember, we are interested in generating a good box, like we saw a few slides ago. And they did a very good job because they could use this box to take these features and use them for 30 clinical and diagnostic tasks. So these features were the building block on which they could, develop downstream applications. And I think that this is really super, super cool. I don't know, is it already 1 year ago? I think so, yes. So a very nice spin-off of Mahmoud Lab is Modela AI. They actually took these capabilities and commercialized them and were acquired by AstraZeneca. A beautiful success story going from academia to the industry. I really look up to Professor Faisal Mahmoud. I think is a role model in our field. Now, another effort in this direction was the creation of Virtuo by Page. This was to honor Rudolf Virchow, which is considered to be the father of modern pathology. Again, what they did was to train data on 100,000 patients to obtain from that of more than 1.5 million slides. This was in the collaboration they had with Memorial Sloan Kettering, and to create a foundation model from which you can create downstream applications. Not surprisingly, they were using Dino 2. Now, the Virtuo model was available for not only by academic institutes, but also by commercial companies like ourselves. So we wanted to take the Virtuo model and adapt it to a specific downstream application. This is what we did. We developed in DeePathology a methodology. We also published a paper, and we tested this methodology on two foundation model. One is the Microsoft's Pro V GigaPath. And you see what's interesting here is that we have what is called the zero-shot or one-shot learning to achieve tissue segmentation. What does it mean? It means that with either with zero annotations or with a single annotation of each category, you can obtain segmentation from scratch. And this is, of course, you need to address the features of the foundation model carefully. Here is what we did with Virtuo. It's a one-shot segmentation using our fseg package. So take a look. This is, of course, a fast forward. So you see that we are using the studio to annotate one example from each category. So this is this one. Okay, we now go to the fseg mode. Okay, and now let's run it. Now again, it's a fast forward, but what's nice about this is that we only retrained things to take the information from Page's virtual model and enabling the segmentation task. And this is, I believe, a fundamental, powerful capability. We put a lot of attention in that, not only us, a lot of people and companies do. Super strong, super important, super strong. Okay. Now, if all of it is so fantastic, so are there any risks? Are there any things that we have to consider before we develop or use foundation models? And these limitations are not only relevant for pathology, they are also relevant for any medical imaging domain. So the first thing is the first thing is data. In order to create a good foundation model, you need a lot of data, but not a lot of data is not enough. You need to have good representative data. And I think that this is super important because back in, I don't know, 15 years ago, or 15 is too much, 10, 12 years ago, you would say that you need large data, large data, large data. So large data is not enough. You need to have high quality data which represents your domain. Second, when you are developing a foundation model for pathology, then you have to think, well, I need to look at different types of staining, different types of scanners, different types of protocol. So why? Because you need to be general. And if you are developing a foundation model in a single site, in a single hospital, then it's not a foundation model, it's a model. It's a model, but it's not a foundation model. Another thing that you have to account for is that you have to monitor the way that it is used. It means that what happens when you are when your foundation model is facing a case that it's never seen? Will it be able to generalize? And if it doesn't, will you get some alerts that it's not capable of generalization? Because you need, when your foundation model fails, you need to know that. Because sometimes if you are using something which doesn't work well, but it doesn't tell you that it doesn't work well, so having a false victory can be more dangerous than a failure. So this is something that you really have to pay attention for. Foundation models use a lot of resources. So I wouldn't create a new foundation model only for having fun. No, it should have a meaning. And I think that this is also correct for usage of resources for advanced AI. Um, you should think, well, that is this effort, is it meaningful, and do I bring new added value to the community, being it research or industry player? And another thing, which is still, I think it's in infancy, is the regulatory barrier. Because foundation models can be super, super powerful, but you need to put them in some kind of a monitored environment so that you are taking the responsibility to make the validation appropriate, to account for different sites, to account for different populations, and last but absolutely not least, privacy. And as someone from a company, I can tell you that kudos to the community. Most of the project that we do, the main obstacle is not the algorithms, is not the resources, is the data, and how you make sure that the data is safe and that patient information is secured 100%. And sometimes, is it coming from the technology side? Sometimes you say, no, I want the data. I really want to move forwards and do things. But I think respecting the privacy of information is crucial, because we need to set the boundaries for having a responsible AI. And even if it means that technology advances a bit slower, this is a reasonable price to be paid. So, Jacek, how are you? How significant is federated learning for the future of digital and computational pathology? This is a good question. I think that federated learning, where you are using multi-sites, where each site, what is federated learning? You want to train a neural network for a specific task, or maybe for creating a foundation model, but you don't want to, you want to that you have 8 data centers, and you want each data center not to share the data with the other participants. So what does it mean? It means that we have a neural network, we start training, we are providing, let's say, we don't get images, that not images are traveling back and forth. What is traveling are weights that are coming from the institutes and the corrections coming from the neural network. So I think federated learning is super, super important. But in a way, if you have a good foundation model that you were able to train on another source of data, such as Dino and Dino2, then it could be that it would play a less crucial role. And honestly, Jacek, to be honest with you, I think making a prediction about AI is something that I would refrain to do, because I don't know, this domain is evolving so fast. It's a bit scary. Let's see. So, foundation models are really, I would say, a huge opportunity. I don't think that the use of foundation models is ended. I think it's only, I think it will gain a momentum. I think, but I think that and I will end in this. Foundation models, the way that I see them, are really another set of tools to achieve solutions, good solutions to problems in computer vision. And in the same way that I'm not throwing away all the classical computer vision methods, nor do I throw away all the classical AI methods. When you have a problem, you can solve, you have, I mean, not as someone who's trying to pursue a PhD, but as someone from the industry. When I have a problem, my motivation would be to solve the problem in the best way with the minimal amount of resources. And if I can, if the problem is simple, I'm not going to take like a whole foundation model to differentiate brown cells from non-brown cells. Okay, there are much, much simpler ways to achieve that. So the important thing is, while we are having more and more complex tools, don't be tempted to use these complex tools. Foundation models are excellent. Let's use them. But let's not forget that there are other excellent tools. And one of the tasks that we have as AI developers is to do the right match between problem and solution to be efficient and to bring value. So in this positive, I would say, statement, I will finish. Again, I want to thank you for joining me. I hope that you can see that I really, really love this synergy between mathematics, computer vision, and the ability to work in this fantastic domain of computational pathology. I don't remember what we have next time, but I hope it will be interesting. And thank you very much for your kind feedback. You will get an email tomorrow with a link to the lecture that I promised you, and also a link to a review paper on foundation models. I'm so happy to see that I'm joined by people from all over the world. I think that doing harnessing technology to try to make the world a little bit better is a mission that we all are trying to do together. And I really appreciate the fact that together we try to do something to improve a bit our sometimes complex world. So thank you all. Looking forward to meeting you again next Tuesday. Ciao. Bye-bye.